We left off introducing this idea of thermodynamics, the study of heat and energy change in chemical reactions. So, the main concept that we're talking about this semester is the first law of thermodynamics, that energy is neither created nor destroyed. That's the central tenet of thermodynamics. What it translates to in reality is that the energy change in the system, usually the chemical reaction, will equal the energy change in the surroundings, the difference being the sign. Another way of thinking about it is that the heat lost by the system is gained by the surroundings. So it's a rather simplistic picture. That there's our campfire, and the heat coming off that campfire, Q, will be proportional or will be equal to the negative of the heat lost by the chemical compound, the wood. So depending on where we draw the line, where we're looking at the system or the surroundings, determines the sign. Heat gained by the surroundings is lost by the system. So if we just focus on the system, again, the system and the surroundings are interconnected, so what happens in the system happens in the surroundings. If we just focus on the system, all of the internal energy of the system, delta E, can be summed up by the heat done by the system and the work done by the system, given the symbols Q and W respectively. So just focusing on Q, the heat, the amount of heat available depends on the mass of material times the heat capacity, a quantity that relates how sensitive a material's temperature changes to added heat, usually given the symbol C or CP or S, depending on how you look at it, but it's a constant, and the temperature change of the system. And again, delta, whatever it is usually equal to X in final minus X initial. Right? So it's always final minus initial. So let's take a look at a piece of metal. I'm just going to take some generic piece of metal. Take a 10-gram piece of metal. I'm going to take a 10-gram piece of aluminum. And it's going to be at 100 degrees centigrade. And we're going to drop that piece of metal into ice water. Now, assuming that we have a whopping excess of ice and water, this 10-gram piece of metal, which starts at 100 degrees centigrade, ends up decreasing down to 32 degrees. Oh, what am I doing, Dan? Not 32. 0 degrees centigrade. Sorry. 0 degrees Fahrenheit. We drop it down into a bucket of water that's 0 degrees centigrade. That piece of aluminum goes from 10 degrees centigrade to 0 degrees centigrade. So the change in the heat of the system, delta E, right, would represent a loss of thermal energy. The system from the aluminum. The aluminum starts hot and ends up going cool. And that heat is lost to the surroundings. So the change in energy of the metal, this would be high heat to low heat, final minus initial, low minus high. Means that the change in energy would be negative. So the delta E in this case will be a negative value. Now, we can define losses of energy by the system as exothermic. Now, it's not the same as temperature. It's loss of heat energy, exothermic. And it's loss of heat energy. And we can define materials that gain heat energy as endothermic. And that's always relative to the system. The system has given up heat energy. So endothermic, and that's again another gain of heat energy. So for a piece of metal, the piece of metal gives up its heat. It has a tendency to drop in temperature. But for chemical reactions that give up thermal energy have a tendency to raise their environment's temperature. We don't think about it, but a piece of metal cooling down is actually warming up the environment. So we always have to look at it with respect to the system for the best gauge. So let's prove that in this case. We can look up in our table the heat capacity of aluminum, and we see that the heat capacity of aluminum is 0.900 joules per gram degree centigrade. That's the heat capacity for aluminum. And so we can use our heat equation. Q will equal the mass, 10.0 grams, times the heat capacity, 0.900 joules per gram degree centigrade, times the temperature change. In this case, delta T would equal final temperature of 0 degrees centigrade minus the initial temperature of 100 degrees centigrade to give us a delta T of negative 100 degrees, which we plug in here, negative 100 degrees, and we multiply that out and we get a Q. Q is equal to negative 900 joules. It says that the piece of aluminum has lost 900 joules. The real question is, where does that energy go? Well, if you're paying attention, you know that it goes into the water. And so, when heat, energy, Q, is absorbed by something else, it has a tendency to raise its temperature. And so rather than looking directly at the metal, we can often use the indirect measurement, not of the system, but we can use the fact that we can look at the surroundings to measure the heat change. This interrelationship between these two is at the heart of what we call calorimetry. Which is, if you remember, we introduced this concept of the calorie last lecture. It is just another heat unit. So calorimetry is heat measurements. And the way you usually do heat measurements is, rather than relying on measuring the system, which is usually, again, the chemical reaction, you measure the surroundings and you change the sign to get the information on the system. So let's just take a look at another problem very similar to this. Calorimetry can be used to measure heat changes, but you can also use this heat equation predictively. So how hot would a 15-gram piece of aluminum at 25 degrees get if you add 138 joules of energy? Now you can add heat to something, a flame for instance, and we wonder how hot this piece of metal would get. We have our bar of metal, Aluminum, 15 grams. And it starts at 25 degrees centigrade. Well, these are heat. How hot would something get? Temperature change. Well, we know Q is related to the heat. Q is equal to the mass times the change in temperature times the heat capacity. Again, this is an inherent quantity central to a material. And for aluminum, that's 0.900 joules per gram centigrade or gram Kelvin. Again, 1 degree centigrade is proportional to 1 degree Kelvin, so you can use Kelvin. It's just like these quantities here. So, if we know the mass of material and we plug in the heat, in this case 138 joules were added, we can figure out that, plug this in, 138 joules will equal 15 grams times 0.900 joules per gram degree centigrade, leaves us with a delta T. Rearranging and solving, change in temperature equal to 10.2 degrees. And it would be a positive 10.2. Again, so delta T is equal to final minus initial, so the T final minus 25 degrees initial will equal 10.2. We can rearrange and solve that. It says that our initial temperature, our final temperature at the end of this will be 35.2 degrees centigrade. So adding 10 joules of energy, 138 joules of energy to a 15-gram block of aluminum raises the temperature a lot, 10 degrees centigrade. This is also how you determine specific heats for many materials. You have a known mass, you add a known amount of heat, and you end up with a temperature change. And from that temperature change, you can calculate heat capacity. It's a common problem in the book. Any three of these you can use to calculate the other. The trick is just having the same units. So, adding heat raises the temperature in some cases. Sometimes removing heat lowers the temperature of the material. Again, that is of the system. If a system loses thermal energy, it will have a negative heat associated with it. So let's take a look at another example. You take a nice big chunk of gold. We'll say 100 grams. 100 grams of gold. And you have it hot. We're going to say that this thing is 288 degrees centigrade. If you take that piece of gold and you drop it down into a cold bucket of water, at 20 degrees centigrade, say 175 grams of water, you drop it into that water, the heat out of the gold will flow out of the gold and lead to an increase in the temperature of the water. So the water temperature will increase to 25 degrees centigrade. Now, what's not 100% obvious is that two things in contact with one another will try to equilibrate their temperature. So if the water's at 25 degrees centigrade, that means the gold is also at 25 degrees centigrade. So in this system, in this gold system, we have a temperature change. The heat in the system is expelled to the environment. Now we see that there's a temperature change in the water. This is an example of calorimetry. we can use the temperature change in the water and the water's known heat capacity to figure out information about the system. Because Q of the system is equal to negative Q of the surroundings. The heat lost by the system is the heat gained by the surroundings. If we know the surroundings behavior, we can figure out the system. So we're going to use this setup to figure out what the heat capacity of gold is. What is the heat capacity of gold? So the way this would read in the book would be a 100-gram sample of gold is at 288 degrees C, is placed into 175 grams of water at 20 degrees C. After equilibrating, the temperature of the water is now 25 degrees centigrade. What is the heat capacity of the gold? And the goal is then to recognize, something is changing. Right? The water is changing. The secret to thermochemistry problems is to not mix up your constants. Right, we have the Q of our system from the Q of our surroundings. So the Q of the system is going to be focused on the gold, whereas the Q of the surroundings is going to be focused on the water. Keep those two separate. And so let's just focus on the Q of the surroundings. How has the water of the surroundings changed? The Q of the surroundings, in this case the Q of the water, will be equal to the temperature change in the water. So the delta T of the H2O will equal 25 degrees centigrade minus 20 degrees centigrade. Final minus initial. Or 5 degrees centigrade. And it's a positive value, which means our Q is positive, which is reasonable. Our temperature is going up in our water. That would mean that it is gaining heat energy. Positive. Q of the surroundings is equal to. And then we have to worry about the mass of the water, 175 grams, which would be the mass of the water, times its heat capacity, 4.184 joules per gram degree centigrade, all times the temperature change of 5 degrees centigrade. Plug that into your handy-dandy calculator, and you get a Q of the surroundings equal to 3,601, well, we'll keep that for sig figs, joules. That's the Q of the surrounding, the heat gained by the surrounding, and it's a positive value. Temperature goes up, positive value, good. What that means is that that heat lost by the surroundings has to be replicated from, has to be lost from the system. So that means that Q of the system would have to be equal to negative 361 joules. And then keeping these two separate, we know that our 100 grams of gold has gone from a temperature of 288 degrees centigrade down to a temperature of 25 degrees centigrade. Again, that's not 100% obvious. When something cools, it cools to the same temperature. So the delta T in that case would be, equal, and this would be for the gold, would equal T final, 25 degrees centigrade, minus 288 degrees centigrade as our starting point, or negative 263 degrees. Our change in temperature is negative 263 degrees. And once we have that, this Q for the system is still equal to change in temperature times the mass of whatever's changing temperature times its heat capacity. And so we can rearrange and solve for the heat capacity. Q of the system, in this case, was negative 361 joules. Our negative change in temperature, negative 263 degrees centigrade. And our mass, in this case, was 100 grams. gives us a value of, and what's nice is notice how the signs cancel. The heat capacity should be a positive, 361. Gives us a value of 0.139 joules per grams degrees centigrade. Notice how the heat capacity of this value is significantly smaller than the heat capacity of water and the heat capacity of aluminum. Gold heats up really quickly and cools off very quickly, very easily. A small amount of heat produces a huge temperature change in the gold. Water, on the other hand, is very resistant to changes in temperature. This is one of the cooler things about water. So large amounts of heat can be stored in water or removed from water. That's why it's used in heating and cooling systems. So this is, again, a practical example of calorimetry. You can use the indirect change in the surroundings to measure the change in the system. So the calorimetry equations are central. Now let's apply it to reactions in the next example.